Good morning, students. Today I am going to discuss about the oxidation state and oxidation number. The oxidation state is the apparent charge present on an atom of element when all other elements are moved in the form ion. I repeat it again. The oxidation number or oxidation state of an atom of element is the apparent charge present on an atom when all other elements are moved in the form of ions. Because we are going to discuss how the oxidation takes place, how the reduction takes place on the basis of this concept. In various complex reactions, we are not able to find out which one undergoes oxidation, which one undergoes reduction. First of all, let us understand the definition of oxidation number or oxidation state. Like in CH4, I would like to find out the oxidation state of carbon. Then I have to remove hydrogen from the carbon. Now this is neutral molecule, therefore this carries zero charge. And hydrogen is less electronegative than carbon, means it is electropositive. It will leave in the form of H positive. How many H positive should be removed? 4. So 0 per mole is this negative sign. 4 into plus 1. This comes out to minus 4. It means in this case the oxidation state of carbon is minus 4. On the other hand, in this case, hydrogen is less electronegative but chlorine is more electronegative. I have to remove hydrogen in the form of plus 1 while chlorine in the form minus 1. As a result, the residual charge or the apparent charge comes out to minus 2. In this case, the oxidation state is minus 2. In this case, I have to remove the hydrogen in the form of plus 1 and chlorine in the form minus 1. In this case, 0. And this classifies the oxidation number and oxidation state is not same as that of a valence. Because zero valency is only in case of noble gases. In this case, you will get plus 2. In this case, you will get plus 4. In different compounds, you will get different oxidation state of a same element. But valency is here is 4, here is 4, here is 4, here is 4, here is 4. Same element has same valency. Valency is the number of electrons lost or gained by an atom so as to acquire noble gas configuration. Where in this case the apparent or the residual charge present. Oxidation state of the same element in different compound is different. No doubt, in some cases you will get a valence and oxidation state may be same. Like here, you will get plus 4, minus 4. But carbon cannot have zero valency, the oxidation state 0. In some cases, you will get the oxidation state in fraction. Valency cannot be in fraction. So, in this way, we have to remove the concept that oxidation state and valency is same. No, it may be same or it may be different. But in this way, to find out the oxidation state is very difficult. We have to follow some method to find out the common oxidation state or average oxidation state. But in case of further complexities, then we will use this method also. And the first rule is the oxidation state of an atom of element in atomic state or in homomolecular state is taken as 0. Sodium, this is atomic state, it has 0 oxidation state. Magnesium, atomic state. Monatomic state, 0 oxidation. But this is homomolecular state. In this case, the oxidation state of hydrogen is taken as 0. This is atomic state, but this is a homomolecular state. In this case also the oxidation state of bromine is taken as 0. In both cases the oxidation state of sulfur is 0. In both cases the oxidation state of phosphorus is 0. In both cases the oxidation of nitrogen is taken as 0. This is the first one. It may be solid, liquid or gas, that is immaterial. Second, in monatomic ion the oxidation state is same as the charge present on ion. Monatomic ion, Na positive plus 1, zinc 2 positive plus. But if in case of Zn, you will get 0 oxidation state. Similarly, in case of Na, here is 0, but here is plus 1. Because this is ion, this is N. P3 negative, minus 3, S2 negative, minus 2, Cl negative. And there are so many monatomic ions. In that case, you will use the oxidation state as charge present on ion. Now, in case of heteroatomic molecule or molecular ion, more electronegative has negative oxidation state, like we did in this case also, and less electronegative or more electropositive has positive oxidation state, like in this case. Fluorine is more electronegative. This has a negative oxidation state and this has positive oxidation state. Oxygen is more electronegative. This has a negative oxidation state and this has positive oxidation state. Oxygen is more electronegative. This has negative oxidation state and this is electropositive. This has positive oxidation state. The oxidation state of hydrogen is taken as +1 when combines with non-metal, but -1 when combines with metal, because metals are more electropositive than hydrogen. The oxidation state of oxygen is generally taken as -2, but in peroxide and superoxide is -1 and -1/2. Oxygen, in this way we find that the oxidation state is generally negative, but oxygen shows positive oxidation state when combined with fluorine, because fluorine is more electronegative than oxygen. The oxidation state of halogen is generally taken as -1 and fluorine always shows -1 oxidation, except in this one. In this case, the oxidation state of fluorine is taken as +1. This is an exception, hypofluorescence. Other halogens in addition show +1, +3, +5, +4, +6, +7 oxidation state, depending upon the type of compound form with which they combine, and so on. Sometimes you have to take up a complete ion. In that case, in case of complete heteroatomic ion, the oxidation state is same as the charge present. In case of sulfate, -2, phosphate, -3, ammonium ion, +1, hydroxide ion, -1, carbonate, -1. Whenever we have to take up the complete ion. The sum of oxidation state is taken as 0 in case of a molecule, in case of neutral species, and in case of molecular ion, the sum of oxidation state is taken as charge present on an ion. Now let us take up these rules and find out the oxidation state of an atom or element in the compounds by following these rules. Very simple rule. Nobody will ask from you what are the rules of the oxidation state to find out oxidation state. You have to apply directly. You have to find the oxidation state or you have to find out which one undergoes oxidation, which one has to undergo reduction. That is again on the basis of oxidation number. Which one undergoes disproportionation, that is also decided on the basis of oxidation number. Like, I would like to find out the oxidation number one rule I left here is the oxidation state of group 1 and group 2 metal in the compounds is taken as +1 and +2 respectively. If any element from group 1 forms a compound, in that case group 1 element will show +1 oxidation state. Means lithium, sodium, potassium, radium, cesium, francium. It combines with it, maybe from with carbon, halogen or nitrogen or oxygen, then they will show +1 oxidation state. In case of group 2, if they combine with any other element, they will show positive oxidation, so +2 oxidation state. Now let us take up the oxidation state of carbon in CHCl3. I will assume the oxidation state of carbon is taken, let it be X. This is neutral molecule. Let it be X. The sum oxidation state should be 0 in case of electroatom. The sum oxidation state is taken 0 in case of a molecule. X plus the oxidation state of hydrogen is taken as +1, and there are 3 chlorine atoms, and in case of chlorine is taken as -1 equal to 0. Then X -2 equal to 0, X is equal to +2. So in this case the oxidation state of carbon is taken as +2. Hydrogen +1 then combines with non-metal is taken as +1, and in case of chlorine is -1. Oxidation state of carbon is CO2. Oxidation state of carbon in C2O4H2. I will assume the oxidation state of carbon is X. Then there are 2 carbon, means 2X plus 4. Oxidation state of oxygen is taken as -2 plus 2 into +1. Hydrogen +1 equal to 0. Then 2x -8 plus 2 equal to 0. Then 2x equal to +6, or x is equal to +3. Then the oxidation state comes out to be +3. The oxidation state of carbon in carbonate, this is molecular height, x plus 3 into -2 equal to -2. In case of molecular ion, the sum of oxidation state is equal to charge present on ion, and charge is -2 equal to -2. Then x equal to -2 plus 6, that is comes out to be +4, and the oxidation state comes out to be +4. The oxidation state of chromium in potassium dichromate. I will assume the oxidation state of chromium X, and here is potassium that belongs to group 1. In case of group 1, I will take up the oxidation state as +1 plus 2 into 2x plus 7 into -2 equal to 0. 2 plus 2x minus 14 equal to 0, or x is equal to +6. Here the oxidation state is taken as +6. oxidation state of manganese in permanganate ion. I will assume the oxidation state of manganese is as X. Then X plus 4 into minus 2 equal to minus 1. Then X is equal to plus 7. The oxidation state of carbon in C2H6O. C2H6O. So 2x plus 6 into plus 1 plus minus 2 equal to 0. Then x is equal to minus 3. Sorry. Then x is equal to, here is plus 4. X is equal to plus 4 by 2 plus 2. The oxidation state of iron in Fe3O4. 3x plus 4 into minus 2 equal to 0. Then 3x is equal to plus 8 or x is equal to plus 8 by 3. Here value comes out in fraction. The oxidation state will be in fraction. Valency cannot be in fraction. The oxidation state of chromium in this case. So, oxidation state of chromium is taken as X plus 4. This is a complete ion. In case of complete ion, we will take valency or the charge present on a complete ion. So, hydroxide ion is minus 1. The sum of oxidation state equal to charge present ion. X is equal to plus 3. It is plus 3. The oxidation state of nitrogen in ammonium carbonate. I will assume that oxidation state of nitrogen is X. So 2 into X plus 4 into plus 1. I have completed this part. 2 here, X, 4 into plus 1, because this combines with non-matter. But this is complete ion, carbonate, plus minus 2. And 2x plus 4 minus 2 equal to 0. Sorry, plus 8. 4 into 2, 8. Then x is equal to minus 6 by 2 minus 3. There is minus 3. Now, on the other hand, the oxidation state of carbon in this molecule, underlined element, carbon. So this is complete ion. Ammonium has plus 1, is 2 into plus 1 plus x plus 3 into minus 2 equal to 0. then X is equal to plus 4. The oxidation state is plus 4. Oxidation state of copper in copper sulfate. So this is complete ion. X plus 2 into plus minus 2 equal to 0 sulfate, or X is equal to plus 2. That is plus 2. The oxidation state of nitrogen in nitric acid, HNO3. Hydrogen plus 1 plus X plus 3 into minus 2 equal to 0. Then X is equal to plus 5. Oxidation state of chlorine in HClO4 plus 1 plus X plus 4 into minus 2 equal to 0. X is equal to plus 7. Now here is plus 7 oxidation state. So in this way, try to find out the oxidation state of the atom of an element from the book recommended by NCERT, and I will discuss in detail next time the Stokes notation, under what condition the species will act as only oxidant, only as a reductant, and under what condition you undergo disproportionation reaction, etc.